Hello, welcome back to ZzScience. Tonight, we're going to take a very slow journey away from the warmth of the sun toward the quiet edge of our solar system. There's no rush. There's nowhere we need to be. We're simply going to drift outward, slowly, and see what happens when familiar things begin to fade. The solar system doesn't end the way a country ends. There's no border, no sign, no moment when you cross from one side to the other and everything changes. It's more like walking away from a campfire on a cold night. At first, you feel the warmth on your face, then on your hands, then less. The light still reaches you, but softer. The heat becomes a memory, and eventually, you're far enough away that you're not sure if you're still in the glow or if you've stepped beyond it. That's what it's like out there. The end of the solar system is not a place. It's a fading, a gradual loss of influence. The sun's gravity, its light, its wind of particles, all of these things reach outward, and somewhere, very far from here, they begin to lose their grip. But where exactly? That depends on what you're measuring. If you measure by light, the sun's glow travels outward forever. It gets dimmer, yes, weaker, but it never truly stops. Photons keep moving. They spread, they thin out, but they don't vanish. If you measure by gravity, the sun's pull also extends outward, theoretically without end. Gravity weakens with distance, but it doesn't cut off. There's no line where it stops. And if you measure by the solar wind, the stream of charged particles that flows outward from the sun, then the boundary is somewhere around 90 to 120 astronomical units from the sun. An astronomical unit is the distance from the Earth to the sun, about 93 million miles. So we're talking about a boundary that sits somewhere between 8 and 11 billion miles away. That's where the solar wind meets the interstellar medium, where the sun's bubble ends and the space between stars begins. But even that boundary is not sharp. It's fuzzy. It moves. It breathes in a way. So when we talk about the end of the solar system, we're talking about something imprecise, something that depends on perspective, on what you think the sun's influence really means. And that's fine, because this journey is not about finding an exact answer. It's about feeling the distance, about understanding what it means to move away from the only star we've ever known. Let's start with what we do know. The solar system, as most of us imagine it, is the sun and the planets. Mercury, Venus, Earth, Mars. Then the asteroid belt. Then the gas giants, Jupiter, Saturn, Uranus, Neptune. Neptune is the farthest planet from the sun. It orbits at about 30 astronomical units. That's roughly 2.8 billion miles. For a long time, people thought that was the edge. Neptune was the last planet, so beyond Neptune was nothing. Or at least, nothing that mattered. But that's not true. Beyond Neptune, there's a lot. It's just very spread out, very cold, very dark, and very far away. The first region beyond Neptune is called the Kuiper Belt. The Kuiper Belt is a disc-shaped region of icy bodies that begins around 30 astronomical units from the sun and extends outward to about 50 or 55 astronomical units. It's similar to the asteroid belt, but much larger and much farther away. The objects in the Kuiper Belt are mostly made of ice, water ice, methane ice, ammonia ice. They're leftovers from the early solar system, pieces that never came together to form a planet. They've been drifting out there, mostly undisturbed, for billions of years. Pluto is in the Kuiper belt, so is Eris, and Makemake, and Haumea. These are called dwarf planets, but really, they're just large Kuiper belt objects. There are probably hundreds of thousands of smaller objects out there too, maybe millions. We don't know. We haven't seen most of them. The Kuiper belt is not empty, but it's also not crowded. If you were standing on one of those icy worlds, you wouldn't see the others. They'd be too far away. Too dim. You'd see the sun, much smaller than it appears from Earth. A bright star, but just a star. And around you, darkness. The Kuiper belt doesn't have a hard outer edge either. It fades. Some objects orbit a little farther out. Some have orbits that are tilted or stretched. Slowly, as you move outward, the number of objects decreases. And then you reach what's called the scattered disk. The scattered disk is not really a separate region. It's more like an extension of the Kuiper belt, but with objects that have been pushed into strange, elongated orbits. These orbits were probably shaped by gravitational interactions with Neptune long ago. The objects swing far out from the Sun, then come back in, then swing out again. Some of these orbits reach hundreds of astronomical units from the Sun. One object, called Sedna, has an orbit that takes it as far as 937 astronomical units from the Sun. That's about 87 billion miles. Its orbit takes more than 11,000 years to complete. We don't know much about Sedna. We've only seen it as a dot of light, a faint signal. We don't know what it's made of, not exactly. We don't know if it has an atmosphere, or moons, or surface features. We just know it's out there, moving slowly through the dark. And Sedna might not even be the farthest. There are hints, statistical hints, not direct observations, that there may be other objects even farther out. Some astronomers think there might be a large planet, several times the mass of Earth, orbiting somewhere in the distant outer solar system. They call it Planet 9, or sometimes Planet X. But no one has seen it. The evidence is indirect. Gravitational tugs, patterns in the orbits of distant objects, clues, not proof. It's possible that Planet 9 doesn't exist. It's possible that the patterns are coincidence, or that something else is causing them. But it's also possible that there's a world out there, massive and cold, circling the Sun in near total darkness, and we just haven't found it yet. That's the thing about the outer solar system. It's so big and so dark that even large objects can hide. When we look outward from Earth, we're looking with light. Telescopes gather light. Cameras capture light. Our eyes see light. But light gets weaker with distance. It spreads out. By the time sunlight reaches the Kuiper belt, it's already very faint. An object in the Kuiper belt receives about 1/1600th the sunlight that Earth does. That's not much, and the light that reflects off those distant objects, back toward us, is even fainter. A tiny glint, a whisper of brightness against the black. So we miss things. We miss a lot. Most of what we know about the outer solar system comes from a handful of observations. A few spacecraft, a few very patient astronomers, years of looking at the same patch of sky, waiting for something to move. It's slow work, quiet work, the kind of work that doesn't make headlines, but it's how we learn. Let's talk about distance for a moment, not just as a number, but as something real, something you can almost feel. When we say that Neptune is 30 astronomical units from the Sun, that sounds manageable. 30. It's a number you can count to. You can imagine 30 of something. but an astronomical unit is 93 million miles. 30 astronomical units is 2.8 billion miles. If you could drive a car at 60 miles per hour without stopping, it would take you more than 5,000 years to reach Neptune. Light, which is the fastest thing we know of, takes about 4 hours to travel from the Sun to Neptune. 4 hours. That means if something happened on the Sun right now, a flare, an eruption, a sudden change, Neptune wouldn't know about it for 4 hours. The light carrying that information would still be on its way. And if you wanted to send a message to a spacecraft near Neptune, using radio waves, which also travel at the speed of light, it would take 4 hours for your message to arrive. And another 4 hours for the reply to come back. 8 hours for a conversation. That's how far away Neptune is. Now imagine going farther. The Kuiper belt stretches from 30 to 55 astronomical units. The scattered disk goes farther. Sedna, at its farthest point, is nearly 1,000 astronomical units from the Sun. 1,000 astronomical units is 93 billion miles. Light from the Sun takes about 5.5 days to reach that distance. 5.5 days. If you were standing on Sedna, at the farthest point in its orbit, and you looked at the Sun, you'd be seeing it as it was almost a week ago. And the Sun would look small, much smaller than it looks from Earth. It would still be the brightest thing in the sky, by far, but it wouldn't look like a disk anymore. It would look like a very bright star, a point of light. The sky around you would be black, not the blue-black of a night sky on Earth, where the atmosphere scatters light, but true black, empty. The stars would be sharp and clear, because there's no atmosphere to blur them. No air, no wind, no sound, just cold. The temperature on Sedna is probably around -400 degrees Fahrenheit, maybe colder. At that temperature, most substances we're familiar with would be frozen solid. Nitrogen, oxygen, carbon dioxide, methane, all of them would be ice. Hard, still. Water ice at that temperature is harder than steel. There's no weather on Sedna. No erosion, not really. No plate tectonics, no volcanoes. Nothing moves except the slow march of radiation from space, which very gradually, over billions of years, changes the surface chemistry. It's a world frozen in time, and it's so far away that even our fastest spacecraft would take decades to reach it. The New Horizons probe, which flew past Pluto in 2015, is currently the fastest human-made object leaving the solar system. It's traveling at about 36,000 miles per hour. At that speed, it would take more than 1,700 years to reach Sedna at its farthest point. 1,700 years. We haven't been sending spacecraft into space for 1,700 years. We haven't been doing much of anything as a species for 1,700 years in a continuous way. So we're not going to Sedna, not anytime soon. But we know it's there, and we know there are others like it, silent, distant, moving slowly through the dark. And beyond them, even farther out, is something we've never seen. The Oort cloud. The Oort cloud is a theoretical shell of icy objects that surrounds the solar system. It's named after Jan Oort, a Dutch astronomer who proposed its existence in 1950. We've never actually seen the Oort cloud. We have no images of it, no direct observations. But we think it's there because of comets. Comets are icy bodies that sometimes fall inward toward the Sun. As they get closer, the Sun's heat causes the ice to sublimate, to turn directly from solid to gas, and that gas forms a glowing tail. That's what we see when a comet passes by Earth, a streak of light, a visitor from the outer dark. Most comets come from the Kuiper belt. Their orbits are relatively predictable. They come around every few decades or every few centuries, and we know roughly where they come from. But some comets appear out of nowhere. They come from random directions. They have orbits that are almost parabolic, meaning they're barely bound to the sun at all. They swing in once from some distant point, and then they leave, never to return. These are called long-period comets, and the only way to explain them is to assume that there's a vast reservoir of icy objects surrounding the solar system, far beyond the Kuiper belt. A cloud of potential comets waiting in the dark. Every so often, something disturbs one of them. Maybe a passing star, or a gravitational ripple, or just chance. And it falls inward, toward the sun. That reservoir is the Oort cloud. If the Oort cloud exists, and most astronomers believe it does, it's enormous. The inner edge of the Oort cloud is thought to begin around 2,000 astronomical units from the sun. The outer edge might extend as far as 100,000 astronomical units, or even 200,000. 200,000 astronomical units is about 3 light years. A light year is the distance light travels in 1 year. It's about 6 trillion miles. 3 light years is 18 trillion miles. That's hard to imagine. Let's try. If you took all the distance from the Sun to Neptune, 2.8 billion miles, and you stacked it end to end, over and over, about 6,400 times, that would be 3 light years. The Oort cloud is so far away that it's closer to the nearest stars than it is to the Sun. Proxima Centauri, the closest star to our Sun, is about 4.24 light years away. The outer Oort cloud is 3 light years away. So if you were standing in the outer Oort cloud, Proxima Centauri would be closer to you than the Sun is. That's strange to think about. You'd still be orbiting the Sun. Technically, the Sun's gravity would still hold you, but barely. You'd be moving so slowly that it would take millions of years to complete one orbit, and the Sun would look like a star. A bright one, but just a star. You wouldn't feel like you were part of the solar system anymore. You'd feel like you were somewhere else, in between, neither here nor there. And yet, you would still be bound, still connected, still, in some faint way, home. The Oort cloud has never been photographed. We don't know how many objects are in it. Estimates range from billions to trillions. We don't know what they're made of, exactly. Probably ice, water, methane, ammonia, the same materials that make up comets. But we don't know. For sure. We don't even know if the Oort cloud is spherical, or disc-shaped, or something else. The models suggest it's roughly spherical, but models are just guesses. Informed guesses, but still guesses. Everything we think we know about the Oort cloud is based on inference, on math, on watching comets fall inward and tracing their paths backward, out into the dark, and asking, where did you come from? And the answer, as best as we can tell, is from very far away. Somewhere out there, in the cold and the silence, there are chunks of ice drifting in slow, wide orbits around the Sun. They've been there since the solar system formed. 4.5 billion years. They've never been warmed, never been lit, never been touched by anything except the faint pressure of starlight and the even fainter pull of gravity. They're waiting, not for anything, just waiting. That's what most of the universe does. It waits. Let's come back for a moment to something simpler. Sunlight. we think of sunlight as something warm, bright, life-giving. And it is, here on Earth. The sun powers almost everything. Plants grow because of sunlight. Animals eat plants or eat other animals that eat plants. Weather happens because the sun heats the air and the oceans. Even fossil fuels, coal, oil, gas, are stored sunlight from millions of years ago. The sun is the reason we're here. But sunlight fades. By the time you reach Mars, sunlight is already weaker. Not by a lot. Mars gets about 44% of the sunlight that Earth does, but enough that you'd notice. The sky is dimmer. The warmth is less. Solar panels work, but they need to be bigger. By the time you reach Jupiter, sunlight is only 4% as strong as it is on Earth. By Neptune, it's 1/9 of 1%. By the Kuiper belt, it's less than that. And by the Oort cloud, well, sunlight is barely distinguishable from starlight. That's what distance does. It takes something abundant and makes it scarce. It takes something obvious and makes it subtle. The sun doesn't disappear. It's still there, still shining, still pouring energy outward in every direction. But from far enough away, it stops being the sun, the center of everything, the source of light and warmth, and it becomes just another star, a bright one. The brightest one in the sky, if you're still within a few light years. But still, just a star. And that changes things, because once the sun is just a star, you're not really in the solar system anymore. Not in the way we usually think about it. You're somewhere else. The outer solar system feels empty. That's the first thing you notice if you imagine yourself out there. The absence. No planets nearby, no moons, no asteroids tumbling past. Just space. Darkness, silence. The word empty isn't quite right though, because space is never truly empty. There's always something: dust, gas, radiation, magnetic fields, particles. But the density is so low that, for all practical purposes, it feels like nothing. In the Kuiper belt, the average distance between objects is measured in millions of miles. You could drift for years without coming close to anything. In the Oort cloud, it's even more sparse. Objects are separated by billions of miles. If you were standing on one of them, you would never see another one. Not with your eyes. Not with a telescope. They'd be too far away. Too dim. You'd be alone. Completely alone. And yet, paradoxically, you'd also be surrounded. Because the Oort cloud is everywhere around you, in every direction. Billions of objects, all slowly orbiting the sun, all invisible to one another. It's a kind of loneliness that's hard to describe. Not the loneliness of being the only one, but the loneliness of being one among countless others, all unreachable. Humans have always been fascinated by edges. The edge of the map, the edge of the known world, the edge of the ocean, the edge of the forest. There's something compelling about boundaries, about the moment when familiar things end and unknown things begin. The edge of the solar system is like that. It's not a cliff, it's not a wall, but it's a transition. A place where the sun's influence fades and something else begins. And we want to know, what's on the other side? Not because there's treasure there, not because it's useful, but because it's there, because it's unknown, because the question itself is interesting. That's why we send spacecraft. Not to find resources, not to colonize, not even, really, to discover specific things, but to see, to listen, to learn what the universe is like when we're not looking at it from our small, bright, warm corner. The Voyager spacecraft, Voyager 1 and Voyager 2, were launched in 1977. Their primary mission was to explore Jupiter and Saturn. Voyager 2 also visited Uranus and Neptune. They sent back images, data, information about the giant planets, their moons, their rings, their magnetic fields. And then they kept going. They weren't designed to leave the solar system, not really. But their trajectories, after passing the giant planets, were aimed outward, away from the sun, into the dark. And because they were still functioning, still transmitting, still powered by the slow decay of plutonium in their radioisotope thermoelectric generators, scientists kept listening. Voyager 1 is now more than 15 billion miles from the Sun, about 165 astronomical units. Voyager 2 is a little closer, about 137 astronomical units. Both of them have crossed the heliopause. The heliopause is the boundary where the solar wind stops, where the pressure from the Sun's outward-flowing particles is balanced by the pressure from the interstellar medium, the gas and dust and particles that drift between the stars. Voyager 1 crossed the heliopause in August 2012. Voyager 2 crossed it in November 2018. They're the only human-made objects to do so. When Voyager 1 crossed the heliopause, something changed. The instruments on board detected a sudden drop in the number of solar particles and a sudden increase in the number of cosmic rays, high-energy particles from outside the solar system. It was a shift, a transition, not dramatic, not loud, but measurable. The spacecraft didn't send back pictures. There's nothing to see out there. Just darkness, just particles. But the instruments listened, they measured, they recorded, and they told us. This is different. This is not the solar wind anymore. This is something else. This is interstellar space. The heliopause is not a fixed boundary. It moves, it ripples. The solar wind isn't constant. It fluctuates. Sometimes it's stronger, sometimes it's weaker. And the interstellar medium pushes back with varying pressure too. So the heliopause breathes. It shifts inward and outward over time, over years, over decades. The Voyager spacecraft crossed it at a particular moment, in a particular place. If they had arrived a few years earlier, or a few years later, the boundary might have been somewhere else. That's the nature of boundaries in space. They're not walls, they're gradients, fuzzy zones, places where one thing gradually becomes another. The solar wind doesn't stop all at once. It slows, it thins, it mixes with the interstellar medium, and eventually, it's no longer recognizable as solar wind. It's just particles, part of the general background. The heliopause is the region where that transition happens. And beyond it, what? Interstellar space. But what does that mean? It means space that is not dominated by the sun. Space where the sun is just one star among many. Where the particles and fields and radiation come mostly from other sources. Other stars. The galaxy itself. It doesn't mean empty. It doesn't mean silent. It means different. The interstellar medium is thin, much thinner than the air on Earth, much thinner than the solar wind even. In the interstellar medium, there might be one atom per cubic centimeter, sometimes less, sometimes a little more. That's almost nothing. But it's not nothing, and over vast distances, even almost nothing adds up. The interstellar medium is mostly hydrogen, some helium, trace amounts of heavier elements, oxygen, carbon, nitrogen, iron. All the elements that were made in the hearts of stars long ago, and then scattered into space when those stars died. We're made of that material. The atoms in your body were once part of the interstellar medium. They drifted through space for billions of years before they came together to form the Sun and the Earth, and eventually you. So the interstellar medium is not foreign. It's not alien. It's where we came from. And the Voyager spacecraft, carrying a piece of us, recordings, images, sounds encoded on golden records, are drifting back into it. Slowly, very slowly. At their current speed, it would take the Voyager spacecraft about 40,000 years to travel 1 light year. The nearest star is 4.24 light years away. So it would take Voyager about 170,000 years to reach the nearest star. Except it's not headed toward the nearest star. It's headed in a different direction, toward a star called AC plus 793888, which is about 17 light years away. Voyager 1 will pass within about 1.6 light years of AC plus 793888 in about 40,000 years. 40,000 years. By then, we'll be different. Humanity, I mean, if we still exist. If we're still recognizable as the species that built Voyager. 40,000 years ago, humans were painting on cave walls. We hadn't invented writing. We hadn't invented agriculture. We were hunter-gatherers, living in small groups, following herds, following seasons. 40,000 years from now, who knows? But Voyager will still be drifting, silent, cold, its instruments long dead, its power source depleted, its signal faded into noise. Just a piece of metal and wire and gold, carrying a message from a species that once looked up at the stars and wondered. Maybe someone will find it, maybe not. It doesn't matter, really. What matters is that we sent it, that we tried. Let's talk about time for a moment, because distance and time are connected out here. We measure distance in space by how long it takes light to travel. A light year, a light hour, a light minute. But we also measure time by how long it takes us to travel. And at human scales, those times are long. The New Horizons spacecraft took 9.5 years to reach Pluto. 9.5 years to travel 30 astronomical units. Voyager 1 took 35 years to reach the heliopause. 35 years to travel 120 astronomical units. If we wanted to send a spacecraft to the Oort cloud, to the inner edge, 2,000 astronomical units away, it would take centuries. Even with our fastest current technology. And if we wanted to send a spacecraft to the outer Oort cloud, 100,000 astronomical units away, well, we couldn't. Not with anything we have now. Not with anything we're even close to building. It would take tens of thousands of years. So, we don't go there. We can't. We imagine it. We calculate it. We infer its existence from the behavior of comets and the mathematics of gravity. But we don't visit. And maybe we never will. Maybe the outer solar system will always be a place we know about but never touch. A place we study from a distance. A place we understand through numbers and models and the faint signals from a handful of spacecraft that have barely scratched the surface. That's okay. Not everything needs to be explored by hand. Not everything needs to be conquered. Some things can remain distant, mysterious, known but not familiar. There's value in that too. The outer solar system teaches us something important. It teaches us that the universe is bigger than we are. That sounds obvious. Of course, the universe is bigger than we are. We've known that for centuries. But knowing it intellectually and feeling it, those are different things. When you think about the Oort cloud, about those trillions of icy objects drifting in the dark, billions of miles apart, completing orbits that take millions of years, you feel the scale. You feel how small we are, how brief. Our entire recorded history, every empire, every war, every invention, every person who's ever lived, spans maybe 10,000 years. The Oort cloud objects have been orbiting for 4.5 billion years. 4.5 billion. We are a flicker, a brief moment of warmth and noise in a universe that is mostly cold and quiet. And that's humbling. But it's also comforting in a way, because it means we're part of something much larger, something that doesn't depend on us, something that existed long before we did and will continue long after we're gone. The solar system doesn't care whether we understand it or not. It doesn't care whether we visit it or study it or name its parts. It just is. And there's a kind of peace in that. Here on ZzScience, we talk a lot about space, about the quiet places, the distant places, the places where human concerns fade and the universe just exists. And the outer solar system is one of those places. It's not dramatic. There are no explosions, no collisions, no sudden events, just slow orbits, slow decay, slow changes that take millions of years. It's the kind of place that invites patience, that rewards slowness, that asks you to stop looking for answers and just observe. And maybe that's what we need sometimes. A reminder that not everything is urgent, that not everything needs to be solved or explained or understood right now. Some things can wait. Some things are content to drift. Let's think about what it would be like to actually be out there. Not as a spacecraft, not as a machine, but as a person. Imagine you're standing on a small icy body in the Kuiper Belt. Maybe it's Pluto. Maybe it's something else. Something we haven't even named yet. You're wearing a spacesuit, of course. Thick, insulated, heated, because the temperature around you is close to absolute zero. -400 degrees Fahrenheit. Cold enough that your breath would freeze instantly. Cold enough that most materials would shatter like glass. But you're safe. For now. You look up. The sun is above you, a bright point of light, much brighter than any star, but still just a point. It doesn't light the landscape the way it lights Earth. It doesn't cast strong shadows. The light is pale, diffuse. Around you, the ground is still. There's no wind, no atmosphere, no weather. The surface is ice, but not smooth ice. It's rough, cratered, scarred by billions of years of tiny impacts. Dust grains, micrometeorites, little bits of rock and ice traveling at thousands of miles per hour, slamming into the surface and leaving marks. The sky is black, pure black, and filled with stars. More stars than you've ever seen. Because there's no atmosphere to scatter the light, no air glow, no light pollution, just stars. Thousands of them, tens of thousands. They don't twinkle, they're steady, sharp, clear. And among them, you might see Earth. If you know where to look, if you have a telescope, or maybe even with your eyes, if you're not too far out. Earth would be a tiny blue dot, barely visible, a pixel of light. And you'd know, really know, in a way you can't know when you're standing on Earth, that everything you've ever cared about, everyone you've ever known, every place you've ever been, it's all on that dot, all of it. And out here, it's so far away that it might as well not exist. That's the perspective the outer solar system offers. It's not comforting exactly, but it's real, and sometimes Real is enough. You crouch down. You touch the surface. The ice is hard. Harder than any ice you felt on Earth. Harder than rock, almost. You pick up a small piece. It's rough, angular, frozen solid. You think, this has been here for billions of years, untouched, unchanged, waiting for nothing. And now, for just a moment, you're here with it. You're part of its story. A tiny, brief part. And then you let it go. It falls slowly in the low gravity and settles back onto the surface. And you stand up, and you look out at the darkness, and you feel small, but also connected. Because this place, as distant and cold and empty as it is still part of your solar system, still part of your home in the broadest sense, still part of the same cloud of gas and dust that collapsed 4.5 billion years ago to form the sun and the planets and everything in between. You came from here, in a way, and maybe, someday, you'll return. Not you specifically, but the atoms that make you up. When the sun dies, billions of years from now, it will swell and shed its outer layers, and some of those layers will drift outward, far outward, into the Kuiper belt, into the Oort cloud, into interstellar space. And the atoms that once formed your body, carbon, oxygen, nitrogen, iron, will drift with them. They'll become part of the interstellar medium again. And maybe, billions of years after that, they'll come together again. In a new solar system, around a new star. And they'll form new worlds, new life. And the cycle will continue. That's what the outer solar system is, really. It's not an ending, it's a transition. A place where the old solar system, the one we know, the one we live in, begins to fade into something else. Something quieter, something colder, something more patient. A place where time moves differently, where distance becomes the main character, where the universe is less about us and more about itself. And maybe that's what we're looking for when we study these distant places. Not answers, not resources, not destinations, but perspective, a sense of scale, a reminder that we're part of something much, much larger than ourselves, and that it's okay to be small. It's okay to not understand everything. It's okay to just drift for a while and see where the journey takes us. Even if the journey has no clear end, even if the boundary between here and there is fuzzy, even if we never arrive. The outer solar system is patient. It's been waiting for billions of years. It can wait a little longer, and so can we. The sun is not quiet. We think of it as steady, constant, a ball of light that rises and sets, day after day, without change. But that's only because we're far away, and because our lives are short. Up close, the sun is violent. It churns, it boils, it throws matter outward in great arcs and loops. Its surface writhes with magnetic fields that twist and snap and reconnect. Plasma rises from the interior, cools, darkens, and sinks back down. Sunspots form and fade. Flares erupt. Coronal mass ejections hurl billions of tons of material into space. The sun is a storm that never ends, and one of the products of that storm is the solar wind. The solar wind is a stream of charged particles, mostly protons and electrons, that flows outward from the sun in all directions. It's not a wind in the way we think of wind on Earth. There's no air, no atmosphere, no sound. It's a wind of particles, invisible, intangible, but real. The solar wind moves fast, about 1,000,000 miles per hour on average, sometimes faster, sometimes slower. It carries energy. It carries magnetic fields. It carries the influence of the sun far beyond the orbits of the planets. And it carves out a bubble in space. That bubble is called the heliosphere. The heliosphere is the region of space where the solar wind dominates, where the sun's magnetic field is stronger than the interstellar magnetic field, where the particles flowing outward from the sun are more numerous than the particles drifting in from the galaxy. It's not a perfect sphere. It's more like a teardrop or a comet, stretched out in the direction of the sun's motion through the galaxy. On the side facing the direction the sun is moving, the heliosphere is compressed, squeezed by the pressure of the interstellar medium pushing back. On the trailing side, it's elongated, stretched into a long tail that might extend hundreds of billions of miles. We call that tail the heliotail. We've never seen the heliotail. We don't know exactly how long it is. We don't know its shape, not precisely, but we know it's there, because physics tells us it has to be. When something moves through a medium, even a very thin medium, it leaves a wake. The solar wind flows outward, and the interstellar medium flows past, and where they meet, they create structure, boundaries, shapes. The heliosphere is one of those shapes. And the edge of the heliosphere, the boundary where the solar wind stops and the interstellar medium begins, is the heliopause. The heliopause is not a surface. You couldn't touch it. You couldn't see it. It's a transition. A region where the density of solar particles drops and the density of interstellar particles rises, where the magnetic field changes direction, where the pressure balances. It's dozens of astronomical units thick in some places. In other places, maybe thinner. It moves. It ripples. It responds to changes in the solar wind and changes in the interstellar medium. The sun goes through an 11-year cycle of activity. During solar maximum, the sun is more active, more flares, more coronal mass ejections. The solar wind is stronger. During solar minimum, the sun is quieter, fewer flares, fewer eruptions. The solar wind is weaker. And the heliopause responds. When the solar wind is strong, the heliopause is pushed outward. When the solar wind is weak, it retreats inward. So the boundary between the solar system and interstellar space is not fixed. It breathes. Slowly, over years, over decades. It's a living boundary in a way. Not alive, of course, but dynamic, changing, responsive. And that makes it hard to study. Because by the time you send a spacecraft to the heliopause might have moved. The Voyager spacecraft didn't set out to study the heliopause. When they were launched in 1977, we didn't even know exactly where the heliopause was. We had estimates, guesses, models, but we didn't know. The Voyager spacecraft were designed to study the giant planets: Jupiter, Saturn, Uranus, Neptune, their moons, their rings, their magnetic fields, and they did that beautifully. Voyager 1 flew past Jupiter in 1979 and Saturn in 1980. Then it used Saturn's gravity to fling itself upward, out of the plane of the solar system, on a trajectory that would take it away from the Sun. Forever. Voyager 2 flew past Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989. Then it too headed outward. Both spacecraft were still functioning, still transmitting data, still powered by the slow radioactive decay of plutonium-238 in their radioisotope thermoelectric generators. So scientists kept listening, and the spacecraft kept talking, very quietly, very slowly, but talking. The signal from Voyager 1 takes more than 22 hours to reach Earth now. 22 hours of traveling at the speed of light. By the time we receive a signal, it's old. The spacecraft has already moved on, already experienced whatever it was reporting. And by the time we send a command back, turn on this instrument, adjust that antenna, it takes another 22 hours for the command to arrive. 44 hours for a round trip. Almost 2 days. That's how far away Voyager 1 is. Voyager 2 is a little closer, about 18.5 hours away. Still, 18.5 hours. When Voyager 1 approached the heliopause, we didn't know exactly when it would cross. The instruments on board were designed decades earlier. They weren't specifically built to detect the heliopause, but they could measure particle density, magnetic field strength, cosmic ray intensity, and those measurements could tell us when something changed. In 2012, Voyager 1 started detecting unusual readings. The number of solar particles, protons and electrons from the Sun, started to drop. The number of cosmic rays, high-energy particles from outside the solar system, started to rise. The magnetic field didn't change direction, not the way scientists expected. That was confusing. The models predicted that when Voyager crossed the heliopause, the magnetic field would change direction. It would flip. Because the interstellar magnetic field was thought to point in a different direction than the solar magnetic field. But it didn't flip. It stayed roughly the same. So for a while, scientists weren't sure. Had Voyager crossed the heliopause? Or was it in some transitional region? Some boundary layer that we hadn't predicted? They debated. They analyzed the data. They ran new models. And eventually, they concluded. Yes, Voyager 1 had crossed the heliopause. The date was August 25, 2012. On that day, Voyager 1 entered interstellar space. It didn't send back a picture. There was nothing to photograph. Just darkness. Just particles. But the instruments recorded the change, the shift, the transition from one medium to another. And we listened. And we learned. 6 years later, Voyager 2 crossed the heliopause. November 5, 2018. Voyager 2 had different instruments than Voyager 1. Some of them were still working. Some had failed over the years. But it had one instrument that Voyager 1 didn't have: a working plasma sensor. The plasma sensor could directly measure the solar wind, the speed of the particles, their density, their temperature. And when Voyager 2 crossed the heliopause, the plasma sensor detected a sudden drop in solar wind particles. A very clear, very sharp drop. One day, the solar wind was there. The next day, it wasn't. That was the heliopause. Voyager 2's data confirmed what Voyager 1 had found, and it added new information. It showed that the heliopause, at least where Voyager 2 crossed it, was sharper than expected, more defined. It also showed that the magnetic field didn't flip at the heliopause. Not completely. The interstellar magnetic field was different from the solar magnetic field, but not opposite, just different. Tilted, rotated, complex. The universe doesn't always behave the way our models predict. That's part of why we explore, to find out where our models are wrong, where our assumptions break down, where reality is stranger, or simpler, or just different than we thought. The Voyager spacecraft are now in interstellar space, but they're still in the solar system. That sounds contradictory, but it's not. Interstellar space is space that's not dominated by the solar wind. Space where the particles and fields come mostly from the galaxy, not from the sun. But the solar system, as we've talked about, extends much farther than the heliopause. The Kuiper belt extends to about 50 or 60 astronomical units. The heliopause is around 120 astronomical units. The Oort cloud, if it exists, extends to 100,000 astronomical units or more. And the sun's gravity? Well, the sun's gravity extends even farther. Gravity doesn't have a boundary. It weakens with distance, but it never stops. Technically, the sun's gravitational influence extends about halfway to the nearest star. That's about 2 light years, about 130,000 astronomical units. So even though Voyager 1 and Voyager 2 have crossed the heliopause, they're still bound to the sun. They're still orbiting the sun, very slowly, very distantly. They're still part of the solar system. They've just entered a different part of it. A quieter part. A part where the sun's voice is fainter, where the galaxy's voice is louder. Let's talk about what the Voyager spacecraft are hearing. Not literally hearing. They don't have microphones. Sound doesn't travel in space. But they're listening. With instruments. With sensors. With antennas that pick up electromagnetic waves and particle streams. And what they're detecting is complicated. Space is not empty. We've said that before, but it's worth repeating. Even in interstellar space, there are particles, atoms, molecules, electrons, protons, cosmic rays. There are magnetic fields, tangled, twisted, flowing. There are waves, plasma waves, electromagnetic waves, oscillations in the density and pressure of the interstellar medium. All of this is invisible, intangible. You couldn't see it or feel it, but it's there. And the Voyager spacecraft are measuring it. One of the most interesting things they found is that interstellar space is not uniform. The density varies. In some regions, there might be 1 atom per cubic centimeter. In other regions, less. In some regions, slightly more. The temperature varies too. Not temperature in the way we think of it on Earth, but the kinetic energy of the particles, how fast they're moving. In some regions of interstellar space, the temperature is a few thousand degrees Kelvin. That sounds hot. But remember, there are so few particles that you wouldn't feel any heat. Heat requires particles to collide with you, to transfer their energy to you. In interstellar space, the density is so low that particles almost never collide with anything. So even though the particles are moving fast, fast enough that we'd call them hot, there's no warmth, just motion. The magnetic field in interstellar space is weak, much weaker than the magnetic field near Earth, much weaker than the magnetic field in the solar wind. But it's there, and it has structure. The Voyager spacecraft have detected changes in the magnetic field, fluctuations, rotations. They've detected waves passing through the interstellar medium, pressure waves, density waves, like ripples on a pond, but in 3 dimensions and moving at thousands of miles per hour. These waves come from various sources: supernova explosions, stellar winds from other stars, the motion of the sun itself through the galaxy. Everything that happens in the galaxy creates waves, disturbances, and those disturbances propagate outward through the interstellar medium, and eventually they reach us. They reach the Voyager spacecraft, and the spacecraft measure them, record them, send the data back to Earth. Very slowly. The data rate from Voyager 1 is about 160 bits per second now. That's slower than the internet in the 1990s. Much slower. Voyager 2 transmits at about the same rate. It takes hours to send back a single image, days to send back a full dataset. But we're patient. We wait, because the information is worth it. The Voyager spacecraft are teaching us what interstellar space is like, what it feels like in a sense. Not what it looks like. There's nothing to see, but what it is. And what it is, mostly, is quiet. Not silent, not empty, but quiet. The solar wind back near Earth is turbulent, chaotic, full of structure and variation and sudden changes. The interstellar medium is calmer, smoother. Things change, but slowly. Over days, over weeks, over months. The Voyager spacecraft drift through it, and the medium drifts past them, and they record the passage. Slowly, patiently, without urgency. Let's think about what it means to leave the solar system, because that's a phrase we use. We say that Voyager 1 has left the solar system, but as we've discussed, that's not quite accurate. Voyager 1 has left the heliosphere. It's crossed the heliopause. It's in interstellar space, but it's still gravitationally bound to the Sun. It's still, in a technical sense, part of the solar system. So what does it mean to leave? Maybe it's not about gravity. Maybe it's about influence. The Sun influences the space around it in several ways: through light, through gravity, through the solar wind, through its magnetic field. Voyager 1 is far enough away that the Sun's light is very faint. The Sun looks like a star, not a disk. It's far enough away that the solar wind has stopped. The heliopause is behind it. But the Sun's gravity is still there, still pulling, still keeping Voyager in a very slow, very wide orbit. And the Sun's magnetic field, although weak, still has some influence. The Voyager spacecraft have detected remnants of solar magnetic field lines even in interstellar space. Tangled. Mixed with the interstellar field, but still there. So Voyager hasn't completely left the Sun's influence. Maybe it never will. Or maybe leaving isn't a binary thing. Not a moment, not a line you cross. Maybe it's a gradient, a fading, a slow transition from being close to being distant. From being dominated by the Sun to being dominated by the galaxy. From home to somewhere else. And maybe Voyager is somewhere in the middle of that transition. Not fully here, not fully there, in between. That's where a lot of interesting things happen. In the transitions, in the boundaries, in the places where one thing becomes another. Because that's where you can see both sides, where you can compare, where you can learn what makes each side unique. The heliosphere is unique. In all the universe, as far as we know, there's only one heliosphere. Only one bubble carved out by our Sun. Other stars have their own bubbles, their own stellar winds, their own boundaries, where their influence stops and the interstellar medium begins. But those are different. Those belong to other stars, other systems. The heliosphere is ours. It's the space that the Sun has claimed. The region where the Sun's particles outnumber the galaxy's particles. Where the Sun's magnetic field is stronger than the background field. It's our home, in a sense, not Earth. Earth is our home in a closer, more familiar sense. But the heliosphere is the larger home, the bubble we live in, the protective shell that the sun wraps around us. Because the heliosphere does protect us. The interstellar medium contains cosmic rays, high-energy particles, protons, electrons, atomic nuclei traveling at close to the speed of light. These particles come from supernovae, from pulsars, from the supermassive black hole at the center of the galaxy, from other galaxies. They're dangerous. Not immediately, not in small doses, but over time, cosmic rays can damage DNA, cause mutations, increase cancer risk. On Earth, we're protected from cosmic rays by two things: the Earth's magnetic field, which deflects some of them, and the Earth's atmosphere, which absorbs the rest. But in space, there's no atmosphere. And beyond Earth's magnetic field, there's no protection, except the heliosphere. The solar wind, flowing outward, creates a barrier. It deflects some cosmic rays. It slows others. It reduces the intensity of cosmic radiation inside the heliosphere. Not by a lot. Maybe by a factor of 2 or 3, but enough to matter. Inside the heliosphere, cosmic ray intensity is lower. Outside the heliosphere, it's higher. Voyager 1 measured this. When it crossed the heliopause, the cosmic ray intensity increased by about 25%. That's significant. It means that the heliosphere is doing something. It's shielding us, at least a little. And if the solar wind ever stopped, if the sun ever went quiet, the heliosphere would collapse. And the cosmic ray intensity at Earth would increase. Not catastrophically, not immediately, but over time it could have effects on satellites, on astronauts, on long-term space missions, maybe even on Earth's atmosphere, on climate, on life. We don't know for sure. We've never seen the solar wind stop, but it's something to think about. The sun protects us in ways we don't always notice, by being loud, by being active, by throwing particles outward constantly without rest. That noise, that violence, creates a quiet space for us to live in. Quieter, at least, than the galaxy outside. The Voyager spacecraft are old now. Voyager 1 was launched in 1977. That's 48 years ago, as of 2026. Voyager 2 was also launched in 1977. A few weeks before Voyager 1, actually. 48 years in space. 48 years of exposure to radiation, to cosmic rays, to micrometeorite impacts, to the cold, to the vacuum. And they're still working. Mostly. Some instruments have failed. Some have been turned off to save power. The cameras were turned off decades ago. There's nothing to photograph out there. Just darkness. The ultraviolet spectrometer is off. The infrared spectrometer is off. The planetary radio astronomy instrument is off. But some instruments are still running. The magnetometer, the cosmic ray detector, the plasma wave sensor, the low-energy charged particle detector. These instruments are still sending data, still telling us what's happening in interstellar space. But the power is fading. The radioisotope thermoelectric generators on the Voyager spacecraft produce electricity by converting the heat from radioactive decay into electrical current. When the spacecraft were launched, the RTGs produced about 470 watts of power, enough to run all the instruments and the transmitter and the heaters and everything else. Now, they produce about 240 watts, maybe a little less. And that number drops every year, by about 4 watts per year. Eventually, there won't be enough power to run the instruments or the transmitter. NASA has been turning off systems, one by one, to extend the mission as long as possible. They turned off the heaters, even though that means some parts of the spacecraft are now far below their rated temperature. Below the temperature they were designed to operate at, and yet they keep operating. The engineers who built these spacecraft in the 1970s built them well, built them to last. They didn't know the spacecraft would still be functioning in 2025. They didn't design them for a 50-year mission. But here we are, and the spacecraft are still talking. NASA estimates that the Voyager spacecraft will run out of power sometime between 2025 and 2030. Maybe sooner, maybe later. It depends on which instruments they turn off, how much power they can save, how long the RTGs last. But eventually, the power will drop below the minimum needed to transmit a signal, and the spacecraft will go silent. They'll still be out there, still drifting, still moving through interstellar space at 38,000 miles per hour. But they won't be able to talk to us anymore, and we won't be able to listen. That will be a strange day, the day we lose contact with Voyager. Because for almost 50 years, those spacecraft have been out there, at the edge of the known, sending back signals. Faint signals, weak signals, signals that take hours to reach us, but signals nonetheless. A voice from the dark, a reminder that we've been there, that we've sent something out into the universe, that we've reached, even if only barely, beyond our home. And when that voice goes silent, we'll still have the data, the recordings, the knowledge, but we'll have lost the connection, the real-time link to the farthest human-made objects, and space will feel a little more distant, a little more quiet. Let's talk about why we do this, why we send spacecraft to the edge of the solar system, why we spend billions of dollars and decades of time to study particles and magnetic fields in a region where no human will ever go. It's a fair question. There's no economic value out there, no resources to mine, no worlds to colonize, nothing that will make life on Earth better in any immediate sense. So why? Part of the answer is curiosity. Humans are curious. We want to know. We want to understand. We see something in the distance and we ask, what is that? We notice a pattern and we ask, why does it do that? We wonder about the edges of things, the boundaries, the transitions, and we can't help ourselves. We have to investigate. That curiosity is not unique to scientists. It's not unique to astronomers or engineers. It's human. Children are curious. They ask why constantly. They explore. They touch things. They take things apart. And some of us never stop. We keep asking why. We keep exploring. We keep pushing outward, into the unknown, because the unknown is interesting. Because not knowing feels incomplete. Because knowing feels good. That's part of it. But there's more. Exploration changes us, not just by giving us knowledge, but by changing our perspective. When we look at images of distant planets, or when we read data from spacecraft in interstellar space, we see ourselves differently. We see Earth as one planet among many. We see the solar system as a small bubble in a vast galaxy. We see humanity as a brief flicker in a universe that is billions of years old. And that perspective is valuable. It makes our problems seem smaller, not unimportant, but smaller. It makes our conflicts seem temporary. It reminds us that we're all on the same planet, in the same solar system, under the same sun. It reminds us that we're connected, not just to each other, but to the universe. We're made of the same atoms as the stars, the same particles as the interstellar medium. the same material as the planets and the comets and the dust. We're not separate from the universe. We're part of it. And exploring the universe is, in a way, exploring ourselves. Finding out where we came from, what we're made of, what our place is in the larger story. That's worth something. Maybe not in dollars, maybe not in immediate benefits, but in meaning, in perspective, in understanding. And maybe that's enough. The Voyager spacecraft carry, on their sides, a golden record. It's a phonograph record, an old technology even when Voyager was launched. A grooved disc that can be played with a needle to produce sound. The record contains sounds from Earth, music, greetings in different languages, natural sounds, whale songs, thunder, wind, laughter. It also contains images, encoded as audio signals, pictures of people, animals, landscapes, diagrams of DNA, maps of the solar system. It's a message to whoever might find it. Not humans. We'll never catch up with Voyager. It's too far away, moving too fast. But maybe, billions of years from now, the spacecraft will pass near another star. And maybe there will be someone there, some other intelligence, some other curious beings, and maybe they'll find the spacecraft, drifting, silent, dead, and maybe they'll figure out how to play the record, and they'll hear our music, our voices, our world, and they'll know someone else was here. Someone else looked up at the stars and wondered. That's optimistic, of course. The odds of anyone finding Voyager are very small. Space is big. The spacecraft are small. The galaxy is vast. Even if another civilization exists, even if they're nearby, within a few hundred light years, the chances that they'd happen to find a small, silent spacecraft drifting through the dark are almost zero. But almost zero is not zero, and the gesture matters. The fact that we tried, the fact that we sent a message, even knowing that it would probably never be received. Because sending it says something about us. It says, we care, we hope, we want to be known. We want to reach out across the void and say, we were here, we existed, we thought, we felt, we created, and even if no one ever hears it, we said it. That's the spirit of exploration, maybe. Not the hope of finding something specific, but the hope of connecting, of reaching, of extending ourselves beyond our immediate surroundings, of being part of something larger. The Voyager spacecraft will outlive us. Not us individually, but us as a species, possibly. Humans might not exist 1,000,000 years from now. We might have changed, evolved, become something else, or we might be gone. But Voyager will still be out there, drifting, silent, carrying our message. It's a strange kind of immortality. Not the immortality of consciousness, not the immortality of memory, but the immortality of presence. A physical object created by humans, continuing to exist long after humans are gone. Moving through the galaxy, slowly, endlessly. A monument, a marker, a trace. We were here. Inside the heliosphere, time feels different. Not literally. Time doesn't speed up or slow down based on where you are. Einstein taught us that time is relative, but only under extreme conditions, extreme speeds, extreme gravity. Inside the heliosphere, time is the same as anywhere else. But psychologically, it feels different. Because inside the heliosphere, we're close to home, close to the sun, close to the planets. Things change. Planets orbit. Moons go through phases. Spacecraft move from one world to another. There's activity, motion, events. Outside the heliosphere, in interstellar space, things slow down. Not literally, but perceptually. The Voyager spacecraft are moving at 38,000 miles per hour. That's fast. Much faster than any car, faster than any aeroplane. But in the context of interstellar distances, it's incredibly slow. At that speed, it takes 17,000 years to travel 1 light year. 1 light year. The nearest star is 4.24 light years away. So even moving at 38,000 miles per hour, Voyager won't reach another star for 70,000 years. 70,000 years. That's an incomprehensible amount of time. 70,000 years ago, humans were still in Africa. We hadn't spread across the globe yet. We hadn't invented agriculture. We hadn't built cities. We hadn't written anything down. We were hunter-gatherers, small groups, oral traditions, stone tools. 70,000 years from now. Who knows what we'll be, if we'll be. But Voyager will still be moving, still drifting, still carrying its golden record, unchanged, unaware, patient. That's the timescale of interstellar space. Not years, not decades, not even centuries. Millennia, tens of millennia, hundreds of millennia. Time on a scale that makes human history look like a footnote. And in that context, what does it mean to explore? What does it mean to send a spacecraft out into the dark, knowing that it will drift for thousands of generations before it reaches anything? It means we're thinking beyond ourselves, beyond our lives, beyond our civilizations, beyond our species, maybe. We're thinking about the universe, about time, about what it means to exist in a cosmos that is so much larger and so much older than we are. And maybe that's the real value of missions like Voyager. Not what they discover, not what they send back, but what they represent. A willingness to think long, to act on timescales that exceed our comprehension. To send something outward, not because it will benefit us, but because it's worth doing. Because the universe is worth exploring, worth knowing, worth reaching toward, even if we never see the result, even if the result is just silence. The heliosphere is a bubble. We've said that. But it's not a static bubble. It's not fixed in place. The sun is moving. Through the galaxy, around the galactic center, the sun orbits the center of the Milky Way, just like the planets orbit the sun. That orbit takes about 225 million years to complete. We call that time period a galactic year. The sun has completed about 20 galactic years since it formed, 20 trips around the galaxy. And as it moves, it drags the heliosphere with it. The solar wind flows outward in all directions, but the sun's motion through the interstellar medium creates asymmetry. On the side facing the direction of motion, the nose of the heliosphere, the interstellar medium pushes back, compresses the heliosphere, makes it smaller. On the trailing side, the tail, the heliosphere stretches out, elongates. The result is a shape that looks a bit like a comet, or a teardrop, or maybe a windsock. We don't have a complete picture of the heliosphere's shape. We've only measured it in a few places. Where Voyager 1 crossed, where Voyager 2 crossed. But models suggest it's asymmetric, stretched, dynamic. And the interstellar medium itself is not uniform. As the sun moves through the galaxy, it encounters regions of higher density and regions of lower density, regions with stronger magnetic fields and regions with weaker fields, and the heliosphere responds. When the sun moves through a denser region of the interstellar medium, the heliosphere compresses, shrinks. When it moves through a less dense region, the heliosphere expands. Right now, the sun is moving through a region called the local interstellar cloud, or sometimes the local fluff. It's a region of slightly higher density than average, not a lot higher, but enough to affect the heliosphere. The local fluff is part of a larger structure called the local bubble, a region of space about 300 light-years across, where the interstellar medium is thinner than average. The local bubble was probably created by supernova explosions, multiple supernovae, over millions of years in the same general region. Each supernova released enormous amounts of energy, blasted material outward, swept up the interstellar medium and pushed it aside. And what was left behind was a bubble, a cavity, a region of lower density. The sun is inside that bubble, moving through it, along with thousands of other stars. And the heliosphere, the sun's bubble, is inside the local bubble. A bubble within a bubble. Its structure all the way down, or all the way up, depending on how you think about it. The galaxy is not homogeneous. It's not smooth. It's lumpy, clumpy, full of structure on every scale. Molecular clouds, supernova remnants, stellar winds, magnetic fields, spiral arms, bubbles and shells and filaments. And all of it is moving, orbiting, colliding, evolving. The sun moves through it. The heliosphere moves with the sun. And the boundary, the heliopause, shifts and ripples and breathes in response. It's a dynamic system, and we're just beginning to understand it. Here at ZzScience, we think a lot about the spaces between things, the space between stars, the space between planets, the space between moments. Because those spaces are not empty, they're not nothing. They're full of potential, transition, change. The heliopause is one of those spaces. It's the space between the sun and the galaxy, between the familiar and the unknown, between home and elsewhere. And it's a space that invites patience, because you can't rush through it, you can't hurry across it. You have to drift, slowly, and listen, and see what the universe has to say. The Voyager spacecraft are listening, not with ears, not with consciousness, but with instruments, with sensors. And what they're hearing is the quiet hum of the galaxy, the background radiation, the cosmic rays, the magnetic fields, the plasma waves. All of it faint, all of it subtle, but real and meaningful, because it tells us what's out there, what the universe is like when we're not looking at it from our small, warm corner. It tells us that space is not a void. It's a medium, a substance, thin, yes, but present. And it's alive in a way, not biologically, but dynamically. It changes, it moves, it responds, and we're part of it. Our sun, our heliosphere, our planets, our spacecraft, all of it embedded in the galaxy, all of it moving through the interstellar medium, all of it connected. And as the Voyager spacecraft drift farther and farther from home, they carry that connection with them, a thread, a link, a signal, faint, fading, but still there, for now. And we listen, and we wait, and we think about what it means to reach outward, not because we have to, but because we can. Because the universe is vast, and we are small. But we are curious, And that curiosity takes us places, strange places, distant places, quiet places, places where time moves slowly, where distance is measured in light years, where the sun is just a star. And maybe that's where we need to go, sometimes, to remember, to see ourselves clearly, to understand our place, not at the center, not as the most important thing, but as part of something much, much larger, something ancient, something beautiful, something indifferent to our existence, but welcoming nonetheless. The universe doesn't care whether we explore it, but we care, and so we do. Slowly, patiently, without urgency, one signal at a time, one measurement at a time, one quiet discovery at a time. And the Voyager spacecraft drift on, into the silence, into the dark, into the space between stars, carrying our message, carrying our hope, carrying a small piece of us, outward, always outward, toward nothing in particular, toward everything in general, toward the future, whatever that future holds, and we watch them go, and we listen, for as long as we can. What is interstellar space? It sounds like a simple question, and we've talked about it already. The space between stars, the medium that fills the galaxy, the region beyond the heliopause. But what is it really? Not as a definition, but as a place, as an environment, as something you could, hypothetically, experience. Interstellar space is not empty. We've said that before too, but it bears repeating, because our intuition tells us that space should be empty, vacuum, nothing. And in a sense, it is vacuum. The density is so low, 1 atom per cubic centimeter on average, that it's closer to perfect vacuum than anything we can create on Earth. But it's not nothing. There are atoms. Hydrogen, mostly. About 90% of the atoms in the interstellar medium are hydrogen. 9% are helium. The remaining 1% is everything else. Oxygen, carbon, nitrogen, iron, silicon, all the elements heavier than helium, created in the cores of stars and scattered into space when those stars died. There are molecules too, not many, but some. In the denser regions of the interstellar medium, molecular clouds, there are complex molecules: water, ammonia, methanol, formaldehyde, even amino acids, the building blocks of proteins. Life's chemistry exists in interstellar space, not life itself, but the raw materials, floating, drifting, waiting. There are dust grains, tiny particles, smaller than the width of a human hair, made of silicates, carbon, ice. These grains scatter starlight. They absorb it. They re-emit it as infrared radiation. They're why distant stars sometimes look dimmer than they should. Why some regions of the galaxy look dark even, though there are stars behind them. The dust blocks the light. Not completely, but enough. And there are magnetic fields. The interstellar medium is not just matter, it's also magnetized. Weakly, but measurably. The magnetic field strength in interstellar space is about 1/10,000,000th the strength of Earth's magnetic field. That's very weak. But over vast distances, even weak fields have effects. They guide the motion of charged particles. They create structure. They influence how the interstellar medium flows and swirls and collapses. Stars form in regions where the interstellar medium is dense enough to collapse under its own gravity. And the magnetic field affects how that collapse happens. How fast? In what shape? So the magnetic field, weak as it is, shapes the galaxy. And there's radiation, not just light from stars, but cosmic rays, high-energy particles traveling at close to the speed of light. Protons, electrons, atomic nuclei, stripped of their electrons, accelerated to enormous speeds by supernova explosions, by pulsars, by the magnetic fields around black holes. These particles travel through the galaxy, through the interstellar medium, through the heliosphere, though reduced in number, through our solar system. Some of them reach Earth. They strike the upper atmosphere. They create showers of secondary particles, muons, pions, particles that cascade downward and occasionally reach the ground. You're being hit by cosmic rays right now. As you read this, as you breathe. Not many, not enough to harm you in any immediate sense. Earth's atmosphere and magnetic field protect you, but they're there. Particles that began their journey in some distant supernova explosion. Thousands of light years away, thousands of years ago. And now they're here, passing through you, continuing onward, into the ground, into the Earth, into space on the other side, continuing their journey. Interstellar space is full of these travelers, these particles with no destination, just motion, just energy, moving through the dark, rarely colliding with anything, just going. And woven through all of this, the atoms, the dust, the magnetic fields, the radiation, is space-time itself, the fabric of the universe, the thing that bends around massive objects, the thing that stretches as the universe expands. We don't see space-time, we can't touch it, but we live in it, we move through it, and it shapes everything. Gravity is not a force, according to Einstein. It's a curvature of space-time. Mass bends space-time, and objects follow the curves. That's why planets orbit stars, why stars orbit the galactic center, why galaxies cluster together. Not because they're pulling on each other, but because they're following the contours of space-time. And in interstellar space, space-time is almost flat, not perfectly flat. There are no massive objects nearby to bend it significantly. No stars, no planets, no black holes. Just the gentle, large-scale curvature of the galaxy itself. The slow bend created by the combined mass of billions of stars. It's a calm place, in that sense. A place where space-time is relaxed. Where the universe is not straining or twisting or collapsing, just being. And the Voyager spacecraft are moving through it, following the curves. Drifting along the geodesics, the straightest possible paths in curved space-time. Not propelled, not guided, just falling. Gently, forever. The Oort cloud is hypothetical. We should remember that. We haven't seen it. We haven't imaged it. We don't have direct evidence that it exists. But the indirect evidence is strong. Comets. Long-period comets. Comets that appear from random directions, with orbits that take thousands or millions of years. Where do they come from? The only explanation that makes sense is a vast reservoir of icy objects surrounding the solar system. Far beyond the planets, far beyond the Kuiper belt, far beyond the heliopause. A cloud, a shell, a spherical distribution of potential comets. The Oort cloud, if it exists, and most scientists believe it does, it's enormous. The inner edge might start around 2,000 astronomical units from the Sun. The outer edge might extend to 100,000 astronomical units. Or even farther. 100,000 astronomical units is about 1.6 light years. That's 40% of the distance to the nearest star. The Oort cloud, if it exists, occupies a significant fraction of the space between our Sun and the next star. It's not dense. The objects are spread out, billions of miles apart, trillions of miles apart. If you were standing on one Oort cloud object, you would never see another one. They'd be too far away, too faint. The Sun, from the inner Oort cloud, would be a bright star, still the brightest thing in the sky, but small, very small. From the outer Oort cloud, the Sun would look like other stars, a little brighter maybe, but not dramatically so. You wouldn't feel like you were orbiting the Sun. You wouldn't feel like you were part of the solar system. You'd feel like you were adrift, in the space between stars, belonging to neither, belonging to both. The Oort cloud objects are probably made of ice, the same materials as comets: water ice, methane ice, ammonia ice, carbon dioxide ice, mixed with dust, silicates, organics. They're leftovers from the solar system's formation. Planetesimals that formed in the outer solar system 4.5 billion years ago and were then ejected by gravitational interactions with the giant planets. Kicked outward, flung into distant orbits. They didn't leave the solar system. The Sun's gravity held them. But barely. They settled into orbits so wide, so slow, that they take millions of years to complete. And there they've remained, for billions of years, frozen, dark, undisturbed, except when something disturbs them. A passing star, perhaps. Stars move through the galaxy, just like the Sun does. And occasionally, another star passes relatively close to the solar system. Not close by everyday standards, maybe a light year away, maybe half a light year, but close enough that its gravity can perturb the orbits of Oort cloud objects. A gentle tug, a slight change in trajectory, and an object that was in a stable orbit, circling the Sun at a vast distance, suddenly finds itself falling inward. Slowly at first, then faster. As it gets closer to the Sun's gravity pulls harder. The object accelerates. By the time it reaches the inner solar system, the region where the planets are, it's moving fast. Tens of thousands of miles per hour. And as it approaches the Sun's heat begins to affect it. The ice sublimates, turns from solid to gas without becoming liquid. The gas streams outward, away from the Sun, pushed by the solar wind and by the pressure of sunlight. And it forms a tail, a glowing tail. Gas and dust, illuminated by the Sun. A comet. We see it from Earth, a bright streak in the sky, moving slowly across the background of stars, night after night. We track it, photograph it, study it, and we trace its orbit backward. We calculate where it came from, and the answer, often, is from very far away, from a distance so great that it must be the Oort cloud. That's how we know the Oort cloud is there, not by seeing it, but by seeing what comes from it. The messengers, the travelers, the icy visitors from the dark. How many objects are in the Oort cloud? We don't know. Estimates range from billions to trillions. Billions, trillions. Those numbers are hard to grasp. 1 billion is 1,000 million. If you counted one object per second, it would take you 32 years to count to 1 billion. 1 trillion is 1,000 billion. It would take you 32,000 years. And we're talking about somewhere between 1 and several trillion objects. Maybe more. All of them out there, in the dark, orbiting the Sun at distances we can barely comprehend. Most of them will. Never fall inward. They'll never become comets. They'll just drift, forever, slowly circling the sun, unaware, unchanging, for billions of years, until the sun dies. The sun won't live forever. It's middle-aged now, about 4.6 billion years old. It has about 5 billion years left. In 5 billion years, the sun will begin to change. It will run out of hydrogen in its core. The fusion reactions that power it, that turn hydrogen into helium and release energy, will slow down. And without the outward pressure from fusion to balance the inward pull of gravity, the sun's core will begin to contract. As it contracts, it will heat up, and the outer layers will expand. The sun will become a red giant. It will swell, grow larger, much larger. It will engulf Mercury, probably Venus, possibly Earth. The inner planets will be vaporized, consumed by the expanding sun, and the outer planets will survive, but changed. Jupiter and Saturn and Uranus and Neptune will be farther from the dying sun than Earth is from the sun now. But the sun will be much larger, much brighter. The outer planets will be bathed in heat. Their atmospheres will churn. Their icy moons will melt. Europa's subsurface ocean will boil away. Enceladus's ice geysers will become steam. Titan's lakes of methane will evaporate. The outer solar system will be warm for the first time in its history. And the Kuiper belt will also warm. The ice will sublimate. The objects will develop tails, temporary atmospheres. For a brief time, astronomically brief, maybe a few million years, the Kuiper belt will be active, alive in a sense. And then the sun will shed its outer layers. It will blow them off, gently, over thousands of years. The layers will drift outward, form a planetary nebula, a glowing shell of gas, lit from within by the sun's remaining core. The core will be small, dense, hot, a white dwarf. It will no longer fuse hydrogen. It will no longer generate energy. It will just glow, radiating away its remaining heat, slowly cooling over billions of years. And the solar system will grow dark. The sun will dim, fade, become a faint ember. The planets will freeze. Their atmospheres will condense, fall as snow, freeze solid. The Kuiper belt will return to cold and darkness, and the Oort cloud will remain unchanged, because the Oort cloud is already cold, already dark, already distant. The sun's death will make little difference to the Oort cloud objects. They'll continue to orbit, slowly, silently, around the white dwarf that was once the sun, for billions more years, until, perhaps, another star passes close and perturbs their orbits, and sends some of them inward, toward the dead sun, toward the frozen planets, where there will be no one to see them, no one to call them comets, no one to wonder where they came from. Just ice and rock falling through the dark, following gravity's pull to nowhere in particular. But these are events that lie far in the future. 5 billion years. That's an almost incomprehensible span of time. 5 billion years ago, the Earth was just forming. The solar system was young. There was no life yet. No oxygen in the atmosphere. No continents. No oceans even. Just molten rock and impact craters and violent collisions. In 5 billion years, Who knows what will exist? Humans almost certainly will not. Not as we are now. We might have evolved into something else, something unrecognizable, or we might be gone. Or we might have spread beyond Earth, beyond the solar system, become something that doesn't depend on the sun. Or we might have created something, machines perhaps, or new forms of intelligence that will outlive us. We don't know. But the universe will continue. The galaxy will continue. The stars will continue to burn and die and be born again from the ashes. And the Oort cloud will continue to orbit, patient, indifferent, waiting for nothing, just being. Beyond the Oort cloud, what? This is where our knowledge fades into speculation. Beyond the Oort cloud is the interstellar medium. We've talked about that. The space between stars. But what else? Are there objects out there that don't belong to any star? Free-floating planets, rogue worlds, ejected from their home systems by gravitational interactions, cast out into the dark. We think there might be. Some models suggest that there could be billions of rogue planets in the galaxy, maybe more rogue planets than stars, drifting, orbiting the galactic center directly, not orbiting any star. Dark, cold, frozen. Some of them might be Earth-sized. Some might be gas giants like Jupiter. Some might even have atmospheres, internal heat sources, radioactive decay, keeping their cores warm. Some might have subsurface oceans, liquid water deep beneath frozen crusts. And if there's liquid water, could there be life? It's possible. Unlikely maybe, but possible. Life that never knew a sun. Life that evolved in darkness. Life powered by chemical energy, not by light. We don't know. We've never seen a rogue planet, not directly, but we've seen hints. Gravitational lensing events. Distant objects that briefly magnify the light from background stars. The magnification lasts for hours or days, then it's gone. And we're left wondering, what was that? A planet? A brown dwarf? Something else? We don't know. The galaxy is full of things we don't know. Between the stars, there might be all sorts of objects, planetesimals, asteroids, comets, dwarf planets. Things that were ejected from their home systems and now wander alone. We'll probably never catalogue them. There are too many, and they're too dark, too distant. But they're there, invisible, silent, adrift, part of the galaxy's hidden population. And somewhere among them, perhaps, are our own lost objects. The Oort cloud might not be entirely stable. Over billions of years, some objects might be perturbed not inward, but outward. Kicked hard enough that they escape the sun's gravity entirely. They drift away into interstellar space, becoming rogue objects themselves. Former members of the solar system, now exiles, wandering the galaxy forever, carrying with them the ice that formed around the young sun, the dust that settled in the early solar system, the history of our origins, spreading it slowly across the galaxy. Maybe billions of years from now, one of those objects will encounter another star, fall into its gravity well, become part of a new solar system, and the ice that formed here, around our sun, will melt there, around a different sun. And maybe it will contribute to an ocean. And maybe that ocean will give rise to life. And that life will never know that the water it depends on came from across the galaxy, from a solar system that died long ago. It's a nice thought, poetic maybe, but not impossible. Because the galaxy is old. Stars have been forming and dying for billions of years, and material gets recycled, shared, mixed. The atoms in your body have been through multiple stars. They've been part of the interstellar medium, part of molecular clouds, part of planets, part of comets. They've traveled for billions of years, and they've ended up here, in you, for now. And eventually, they'll move on, become part of something else. That's the nature of the universe. Nothing is permanent. Nothing is isolated. Everything is connected. Everything is in motion. Everything is part of the cycle. Gravity is patient. That's one of the things the outer solar system teaches us. Gravity doesn't rush. It doesn't demand. It doesn't force. It just pulls, gently, constantly. And over time, over vast amounts of time, that gentle pull shapes everything. Orbits, tides, the structure of galaxies, the formation of planets, all of it governed by gravity. And gravity's reach is long, technically infinite. Gravity doesn't have a cutoff distance. It weakens with distance, but it never goes to zero. So the sun's gravity, weak as it becomes, extends outward, past the heliopause, past the Kuiper belt, past the Oort cloud. How far? It's hard to say exactly, because at some point the sun's gravity becomes so weak that other forces dominate. The gravity of other stars, the gravity of the galaxy itself. The sun's gravitational influence is thought to extend to about 2 light years. That's about 130,000 astronomical units. Beyond that, an object would be more influenced by nearby stars than by the sun. So that's the true boundary of the solar system. Not the heliopause, not the Oort cloud, but the distance at which the sun's gravity stops being the dominant force. 2 light years. And even that boundary is fuzzy, because gravity doesn't stop, it just fades, gradually, asymptotically. There's no line, no moment when you cross from one side to the other, just a slow transition. A gradual shift from being dominated by one star to being dominated by the collective gravity of many stars. From being part of the solar system to being part of the galaxy. And in that transition, there's ambiguity. There are regions where the sun's gravity and the galaxy's gravity are roughly equal, where you're not quite sure what you're orbiting, where the answer is both, and neither. That's the true edge of the solar system. Not a place, not a boundary, but a question. We've been thinking about the solar system as something that ends, a sphere, a bubble, a region with a boundary. And in some senses, that's true. The heliosphere has a boundary, the heliopause. The sun's gravitational dominance has a boundary, roughly 2 light years. But in another sense, the solar system never ends, because the sun is part of the galaxy, and the galaxy is part of the universe. And the solar system, the galaxy, and the universe are all connected. The material that makes up the solar system came from the galaxy, from previous generations of stars, from molecular clouds, from the interstellar medium, and eventually the material in the solar system will return to the galaxy. When the sun dies, when the planets are scattered or vaporized or frozen, the atoms will disperse, drift outward, rejoin the interstellar medium, and they'll become part of something else, another star, another planetary system, another world. The cycle continues. So the solar system doesn't end. It transitions. It transitions from one state to another, from a system dominated by a single star to a collection of atoms drifting through the galaxy. And maybe that's a better way to think about it, not as something with boundaries, but as something with phases. Right now, we're in the active phase. The sun is shining, the planets are orbiting, life exists. Eventually, we'll transition to a dormant phase. The sun will dim, the planets will freeze, life will end. And then, much later, a dispersed phase. The sun will be gone, the planets will be scattered, the atoms will drift. And then, perhaps, a recycled phase. The atoms will come together again, form new stars, new planets, new life, different worlds, different stories, but connected, always connected, to what came before, to us, in a way we'll never know, but connected nonetheless. That's the deep time perspective, the view from billions of years, where individual stars and planets and civilizations are just moments in a much longer story, brief flickers of organization in a universe that is constantly reorganizing. And from that perspective, the question of where the solar system ends becomes less important, because the solar system is not a separate thing. It's part of a continuum, part of the galaxy's ongoing process of creating and destroying and creating again. And the boundary, wherever we choose to draw it, is arbitrary, useful for some purposes, but not fundamental, not real in the deepest sense. Because the universe doesn't recognize boundaries. It just is, flowing, changing, continuing. And we're part of that flow. For now. The Voyager spacecraft will drift for a very long time. Even after their power runs out, even after they go silent, they'll continue on their trajectories, unchanged, unguided, just objects, metal and wire and gold, following the laws of physics. Voyager 1 is headed in the general direction of the constellation Ophiuchus. It will pass near a star called AC plus 79 3888 in about 40,000 years. It won't get very close, about 1.6 light years. That's still very far. But it will be the closest Voyager 1 comes to another star for a long, long time. After that, it will continue on, into the broader galaxy. Voyager 2 is headed toward the constellation Andromeda. It will pass near a star called Ross 248 in about 40,000 years, at a distance of about 1.7 light years. And then it too will continue. Both spacecraft are moving at about 3 astronomical units per year. That's about 280 million miles per year. It sounds fast, but on galactic scales, it's incredibly slow. The galaxy is about 100,000 light years across. At their current speed, it would take the Voyager spacecraft about 2 billion years to cross the galaxy. 2 billion years. The galaxy itself rotates. The Sun orbits the galactic center once every 225 million years. So by the time Voyager crosses the galaxy, if it crosses the galaxy will have rotated almost 9 times. Everything will be different. Stars will have formed and died. Spiral arms will have shifted. The distribution of matter will have changed, and Voyager will still be drifting, silent, dead, forgotten. Unless something finds it. That's the romantic thought, isn't it? That someday, billions of years from now, another civilization will encounter one of the Voyager spacecraft. They'll bring it aboard, study it, figure out what it is. They'll find the golden record, decode it, play it, and they'll hear our voices, our music, our message. And they'll know We were here. It's a beautiful idea, but the odds are very, very small. The galaxy is vast. The Voyager spacecraft are tiny. The chances of another civilization finding them are almost zero. Almost, but not quite. And that almost is enough to make it worth doing. Because even if the message is never received, we sent it. We said, "This is who we are. This is what we've created. This is what we value." And we sent it out into the universe, not knowing if anyone would ever hear it, but hoping, always hoping. That's very human, that hope, that reach toward connection, even across impossible distances, that willingness to try, even when success is unlikely. Maybe especially when success is unlikely, because the trying itself means something. It says something about us, about our values, our curiosity, our loneliness maybe, our desire to be known, to be remembered, to matter, even in a universe that is indifferent to our existence. We matter to ourselves, and so we reach out. We send signals, we build monuments, we create art. We tell stories. We say, "We were here. We existed. We thought and felt and wondered. And maybe no one will ever know. But we did it anyway, because it mattered to us. And that's enough." Science is often about finding answers, but sometimes it's about learning to live with questions. The outer solar system is full of questions. How far does the Oort cloud extend? Does Planet 9 exist? What is the shape of the heliosphere? What lies beyond? We don't know, and we might never know. Some questions require technology we don't have yet, spacecraft that can travel faster, telescopes that can see dimmer objects, instruments that can measure from farther away. Maybe we'll develop that technology. Maybe in 50 years, maybe in 100, or maybe not. Maybe some questions are too expensive to answer, too difficult, too far beyond our reach. And that's okay, because the value of exploration is not just in the answers. It's in the process, in the asking, in the wondering. It's in the slow accumulation of knowledge, the gradual refinement of our understanding. It's in the journey itself, not the destination, because often there is no destination, just more questions, deeper mysteries, farther horizons. And that's not a failure. That's the nature of the universe. It's bigger than we are, older than we are, more complex than we can fully comprehend. And we're okay with that. We don't need to understand everything. We don't need to answer every question. We just need to keep looking, keep wondering, keep reaching, and see where it takes us. The outer solar system is a place of transitions, from light to darkness, from warmth to cold, from the familiar to the strange, from the sun's domain to the galaxy's domain, from the known to the unknown. And transitions are interesting, because they're neither one thing nor the other. They're both, and neither. They're in-between places, liminal spaces. And liminal spaces have a certain quality, a certain feeling. They're uncertain, ambiguous, open to interpretation. They invite reflection, contemplation, patience, because you can't rush through a transition. You have to experience it, slowly. You have to notice the changes, the gradual shifts, the subtle differences. You have to pay attention. And if you do, if you slow down and really observe, you see things you wouldn't otherwise notice. Details, patterns, connections, things that are easy to miss when you're focused on the destination. when you're just trying to get from here to there. But if you let yourself be in the transition, if you accept that you're in the in-between, then the transition becomes the journey, and the journey becomes valuable in itself. That's what the Voyager spacecraft are doing, whether they know it or not. They're in the transition, between the solar system and the galaxy, between the sun's influence and the stars' influence, between home and elsewhere. And they're taking their time, drifting, observing, measuring, sending back what they find, for as long as they can. And we're listening for as long as we can. And we're learning, not just facts, not just data, but perspective, a sense of scale, a sense of time, a sense of our place in the universe. And maybe that's the real gift of these distant places. Not resources, not answers, but perspective. A reminder of how vast the universe is, how old, how patient, how much there is that we don't know, that we can't know, and how small we are, how brief, but also how remarkable, that we exist at all, that we can wonder, that we can explore, that we can send machines to the edge of the solar system and beyond, that we can listen to their faint signals and learn from them, that we can imagine what lies farther out, and wonder what it would be like to go there, even if we never do. The wondering itself is valuable, the imagining, the reaching, the refusal to accept that there are places we can't go, questions we can't ask, mysteries we can't explore. Even if it's true, even if there are limits, we push against them, gently, patiently, and sometimes the limits move. Sometimes we discover that what we thought was impossible is just difficult, that what we thought was beyond our reach is just far. And so we keep reaching, one signal at a time, one measurement at a time, one small step at a time, into the dark, into the unknown, into the silence, carrying our curiosity with us, carrying our hope, carrying a small flame of consciousness into a universe that is mostly empty, mostly cold, mostly dark, but not entirely, because we're here and we're looking. And as long as we're looking, the universe is not entirely dark, at least not to us. At ZzScience, we often talk about sleep, about rest, about letting go. And there's something about the outer solar system that invites that, a kind of letting go. Not giving up, but releasing the need to control, to understand, to arrive, accepting that some journeys don't have destinations, that some questions don't have answers, that some places are meant to be distant, mysterious, unknown, and that's okay. Because the universe is not here for us. It doesn't exist to be understood or explored or conquered. It just exists, and we're fortunate enough to be part of it, to witness it, to wonder about it, for a brief moment, cosmically speaking. And when that moment is over, when our sun dies, when our planet freezes, when our species is gone, the universe will continue. The galaxy will continue to rotate. Stars will continue to form and die. The interstellar medium will continue to drift and flow and coalesce. And the Oort cloud, if it still exists, will continue to orbit around whatever remains of the sun, slowly, silently, patiently, unchanged, indifferent, waiting for nothing. And maybe there's comfort in that, in the idea that the universe is bigger than our concerns, older than our worries, more enduring than our fears, that it will continue, regardless, that our presence, or absence, makes little difference to the cosmos. We're not the center, we're not the purpose, We're not the point. We're just here, for now. And that's enough. It has to be. Because it's all we have. This moment, this planet, this solar system, this tiny corner of the galaxy, and the opportunity to look outward, to wonder, to explore. Not because we'll find all the answers, but because the questions are beautiful, and the journey is worth taking, even if it leads nowhere in particular, even if it ends in silence, even if we never arrive. The reaching itself is meaningful, the trying, the wondering, the slow, patient accumulation of knowledge, the signals sent across impossible distances, the machines drifting through the dark, the human voices encoded on golden records saying, "We were here, we wondered, we tried." That's our message to the universe. Not a grand proclamation, not a claim of importance, just a whisper, a small voice in the vast dark, saying, "Hello, we existed." We looked up at the stars and wondered what was out there. And we tried to find out, as best we could, with the tools we had, with the time we had. We tried, and we're still trying, for now, for as long as we can, until the power fades, until the signals stop, until the voices go silent. And then we drift into the dark, into the silence, into the unknown, joining the Oort cloud, joining the rogue planets, joining the dust and gas and ancient photons that fill the space between stars, becoming part of the galaxy, becoming part of the flow, becoming part of the story that has no ending, just continuation, just change, just the slow, patient unfolding of time. And that's okay. That's enough. Because we were here. We wondered. And we reached. And in reaching, we touched something vast, something ancient, something beautiful. The universe itself. Not to possess it, not to conquer it, but to be part of it, to witness it, to honor it with our attention. And maybe that's all exploration really is. Not the pursuit of answers, but the act of paying attention, of looking closely, of listening carefully, of being present, here, now, in this moment, in this place. At the edge of the no, looking outward, into the mystery, into the silence, into the endless, patient dark, and finding, in that darkness, not answers, but connection to something larger than ourselves, to the universe, to the flow of time and matter and energy that connects everything, from the smallest atom to the largest galaxy, from the briefest moment to the deepest time. We're part of it, all of it, and it's part of us. And maybe that's the real boundary. Not between the solar system and interstellar space, not between the sun's influence and the galaxy's influence, but between separation and connection. Between thinking of ourselves as isolated and recognizing that we're woven into the fabric of everything. There is no edge, really, no boundary, just transitions, gradients, flows, one thing becoming another, constantly, endlessly. And we're in that flow, moving with it, shaped by it, part of it, from the beginning until the end, and beyond, into whatever comes next, whatever form the atoms take, whatever patterns they create. The universe continues, and so do we. In a way, not as individuals, not as a species, but as participants in the ongoing process of existence, as small threads in an unimaginably vast tapestry. Brief, bright, meaningful, for now. And that's enough. It's more than enough. It's everything.